On January 19, 2012, the T-WiSE crew visited the Perimeter Institute for Theoretical Physics in Waterloo, Ontario. This institute is an international focal point of cutting-edge scientific research and educational outreach. This Week in Science and Education is presented in association with the Science Coordinators and Consultants Association of Ontario. Visit their website at sccao.ca.
This Week in Science and Education is brought to you in part by the University of Western Ontario, www.uwo.ca. We thank them for their support. This Week in Science and Education is also brought to you by Laurentian University. Check out Laurentian at laurentian.ca. We thank them for their support.
Hey everybody, it's time for This Week in Science and Education. This is your host, Kevin Cougler. We are live today at the Perimeter Institute in Waterloo. We're going to find out all sorts of fascinating things about physics and in particular cosmology, if I'm not mistaken. Joining us is Matt Johnson. He's our special guest today. He's a postdoc here at the Perimeter Institute. But of course, before we get to him, let's introduce Colin Jagoe from the 4th of Pioneers District School Board.
As always, live and in person this time. This is awesome.
I'm here.
I got to tell you, when you told me we were coming down to the Perimeter Institute, I got really excited. Because I love astronomy, I love physics, and I love the theoretical side of it. So I've never had the opportunity to come in, so I'm really excited to talk to you. Just glad to be here.
Well, let's get right to it then, since we have Matt here, and he's going to answer all sorts of questions. So Matt, just to get started, give us an idea of how you got to be where you are today, and exactly what is your role here at the Perimeter Institute?
Well, I got interested in physics probably pretty late in the game, maybe in college. I wanted to be a writer when I was in high school. That was my passion, and then I took a course on environmental modeling and calculus and ecology. And I really found the mathematics to be really beautiful and interesting. And there at the end of the class there was a project that basically said pick whatever project you want to do that involves calculus and these things. Right. And I had kind of been interested a little bit in popular science books, and I wanted to figure out how stars work.
Sure.
So during this project, I looked into how stars work, how stars burn elements like hydrogen and helium, and etc. And then by the end of that, I was just pretty much sold on physics as being really interesting, and the mathematics as being really nice. And then of course, I finished college and I majored in physics.
Right.
And from college, I went on to graduate school. I did my PhD at University of California, Santa Cruz.
Okay.
So that was a 5-year process.
Right.
You take classes for a few years on more advanced topics, and then you do a bunch of research projects, and then you write a thesis, which is sort of the synthesis of all your research projects. And then after that, you basically go on to do research somewhere. And cut your teeth so that maybe someday you can hopefully be a professor in a university. So this is part, now I'm a postdoc here at Perimeter Institute, and basically my job is to do research in physics, and also you can teach, you can get involved in different things, and but yeah, bread and butter of my life is doing research.
You mentioned a little bit about your career path. One thing that I always like to ask people is, when you're talking about how you get to be where you are today, was there somebody along the way, like a high school physics teacher or a friend or a mentor, that was really influential upon you that helped steer you in this path, or how did that occur?
Well, so after I took that class in college, I went to a pretty small college. There were maybe about 1,000 or 2,000 students.
Okay.
And so there really weren't that many people interested in physics per se, just because it was a pretty small
1% or
body
so
of people.
Yeah,
like 2.
Okay.
Yeah. So
2 people or 2%?
2 people. Yeah.
Okay.
So I had a fantastic professor in college who really took an interest in me and you know, in inspiring me and guiding me and telling me what kind of things are interesting and where I can find out more about things. And
You want to share
she
the
was,
name?
oh yeah, her name is E.J. Zita, and she was extremely influential in you know, why I found things interesting and you know, continued to do them. And very encouraging of my next steps in life.
Absolutely, that's really cool. I'm thinking about the math connection, because one of the things, we very often don't talk about math on the show. We talk about science, but we always talk and get around to the interdisciplinary nature of science, how really no subject exists in a vacuum, right? You have to learn everything. But I find it fascinating that what really sparked your interest was sort of a class on things like modeling ecology, right? But using the math in maybe a way that you hadn't considered before. Was that part of it, that you sort of saw, geez, I didn't know you could do that with math? Was that maybe part of it?
Yeah, it's pretty incredible. I
Yeah.
mean, with some small set of tools, you know, like taking one semester of calculus, you can really, you know, think about so many different systems.
Right.
It doesn't have to be
Right.
just ecology
Yeah.
or physics, but you know, like how gravity works and you know, how waves propagate on lakes, and you know, I mean, just pretty much anything you can think of that we see around us, you can describe using the equations that you get from basic calculus.
Basic calculus. Keep the math,
Yeah,
kids.
that's right.
So what is your area of research, and what do you sort of study while you sit here at the Perimeter Institute in Waterloo?
Yeah, so I'm interested in early universe cosmology. So cosmology is basically the study of the structure, evolution, and origin of the universe as a whole. So you really look at the universe as a, you know, system. And I study the very early part of that evolution. That's what I'm most interested in.
Define very early for us.
Okay, so fractions,
I know the answer.
very small fractions of a second after the Big Bang.
Okay, excellent.
So
After the theoretical Big Bang, or
After
after
the-
the proven Big Bang?
not after the theoretical Big Bang.
Okay.
So that's the interesting thing.
Okay.
You know, we'd like to know, first of all, what do the mathematics allow?
Right.
We have theories of the, you know, how gravity works, which Einstein came up with, general relativity.
Yeah.
We have theories for, you know, how the different things that inhabit the universe work, like, you know, electricity and magnetism,
Sure.
and you know, the stuff that we're made out of.
Yeah. Yeah.
And given that set of rules, it's interesting to ask, well, just what's possible?
Right.
And then once you know what's possible, you can ask, what is it possible to know? So if we go out and we actually observe galaxies and different things, different properties of the universe, how many of those different ideas that are allowed are actually consistent with what we see?
Right.
And is it possible to sort of prove or to know with some degree of certainty what actually happened out of all those lists of possibilities?
Right.
And that's what I'm most interested in, is just
So-
figuring out.
You're sort of at the intersection between straight theory in doing math and figuring out what's possible. But then you also, if I'm hearing this correctly, want to back it up with some observational evidence. We think this is possible, so let's go see if it's there, which means that it's not just possible, but it exists. Is that sort of how I take where your intersection research is?
Yeah, that's right.
Okay.
So it's kind of like being a historian, right? There's
A really,
events.
really old
a
historian.
really old historian. Yeah, exactly. You know, there's some partial documents that you have about certain events that might have occurred, and you've got little pieces of evidence, and then, you know, you think about, well, how would those people that lived during that time have thought, and you know, what were their lives like, and things like that, and you're trying to piece together what actually happened, given what you know.
If you were to describe to a high school student, this is what I did today.
Day in the life.
What would be the sort of the typical day? Yeah.
Yeah. So, well, you talk a lot to your colleagues. that's a big thing.
Well, it's problem solving, right?
It's
in
problem
a lot of
solving,
ways.
yeah.
It is, yeah.
Yeah. So you know, there's outstanding questions, some mystery about how an equation works, or what a particular solution to a set of equations means, and you know, you find your friend, and he's an expert in this particular thing, and you tell him, okay, well, this is kind of how I think it works, and then you work through it together, and you know, the collaboration is a huge part of what you do.
Sure.
And then, of course, you disappear into your office and you read things and you try and
make sense.
of how to solve problems and then how to interpret the answers. And,
you said something really interesting. First of all, you talked about the mystery. I love talking to students about the mystery and the wonder and the questions that you come up, because in my view of teaching, the questions are very often more important than the answers. Because a good answer gets more questions, which brings me to your point where you said, I've got a solution to a problem, but then we talk about what the solution means, because that then generates another set of questions. So it's, in my mind, it's really that inquiry process of questions driving questions, and digging, which is just fascinating.
Absolutely.
Right. Okay, awesome.
How would you describe the Big Bang Theory to, say, a 10-year-old that might be listening in a grade 5 class? Where do you begin with that? How do you describe that?
So if you look around us now, we see that distant galaxies are moving away from us.
If I look around us, you say look around us in the hundreds of millions of light years around us.
Yeah,
so
very big
that's
scales.
the physics and cosmologist's local neighborhood,
Right,
as opposed to Waterloo kitchen. It's a very different scale.
Right. So other galaxies, not even just outside our solar system, but other galaxies really far away. Yeah.
Yes. Yeah.
Thousands or millions of light years away.
Yeah.
And you look at these galaxies and you realize that in every direction you look, they're moving away from us.
Right.
And the way that we infer that they're moving away from us is through something known as the Doppler effect. So when an ambulance drives by you hear the pitch of the siren go down, and that's due to something called the Doppler effect, because the ambulance is moving away, and then therefore the sound waves get stretched.
So let me just interrupt you right there for the sake of the younger listeners. So are you saying that you can listen to another planet like Saturn and it emits a sound and you can tell that it's getting further away from us?
No, you can see the light. And light, just like sound, is a wave.
Okay.
And so you can see that light is getting stretched by these galaxies moving away from us. And they're all moving away from us. So if you extrapolate that back in time, then they must have been closer together. And if you go back even further in time, they were closer together still, until you get to the point where, everything was on top of each other. And so the density of the universe had to have started really large, and then got less and less and less until we get to where we are today. And if you extrapolate that back far enough,
eventually come right back to here.
That's right.
Okay.
That's right.
To your question, good sir. However, before you get to that, we're going to take a quick commercial break to thank our sponsors. We'll be right back with Colin's questions right after this in 2 minutes. Don't go away, everybody.
This Week in Science and Education is brought to you by Sheridan Institute of Technology and Advanced Learning. At Sheridan, students shine brighter. Check out sheridanc.on.ca.
And we're back. Thanks everybody for sticking with us. We're talking with Matt Johnson here from the Perimeter Institute in Waterloo. And right before we broke for a commercial, I interrupted Colin, who's about to ask one of his usually brilliant questions. Colin.
I don't know if it's brilliant. It's more, when I come to a place like this and I talk to brilliant guys like Matt, I have the questions that burn through me. And one of the things I'm hoping we can maybe talk about a little bit is the Large Hadron Collider in Switzerland, which is a big news story now, and it's over the last few years as it's been constructed and as it's been turned on. There's been lots of positive and interesting press about it, but more recently they've announced some preliminary results that seem to suggest, correct me if I'm wrong on this, but seem to suggest that they're narrowing in on this legendary Higgs boson particle. So my question is, if you can explain to us what in heaven's name the Higgs boson is, and why it's so important that we find out exactly where it is and if it exists.
Yeah. So
this is the God particle.
It's the one that's, again, I don't like that name because I think it has a whole other connotations to it, right? But it's a very interesting piece of a very important puzzle, as I understand it. So maybe you can sort of explain that to my brain.
Yeah. So stuff has mass.
Yes.
And the fundamental question is why?
Is why? Yeah, right? Absolutely.
And the best answer that we think we have is this thing called the Higgs Mechanism. Okay, which is related to the Higgs boson.
Okay.
So the Higgs Mechanism basically states that there is this stuff, and this stuff permeates the whole universe, and normal matter like electrons and protons and atoms and whatever, it all interacts with this stuff. And in doing so, it gets imbued with a mass.
Okay.
And that's why electrons and protons and whatnot have mass.
So is it? I keep trying to wrap my brain around it. Is it kind of like like a sticky substance that sort of slows things down, and that's where the mass comes from, or is it something else? Like I've been trying to come up with an analogy in my head.
That's a
Is
reasonable.
that sort of getting.
That's a reasonable way to say it. That's
Okay.
right. It's like a viscous fluid or something. You know, and
Okay.
you drag as you move through it.
Yeah, so mass is the drag
Yeah.
through this Higgs stuff.
Yeah. Yeah.
Okay.
And you know, just like a pond or something, you can disturb it. So you can
Sure.
you can you know, tweak this stuff that's
Mhm.
everywhere,
Mhm.
and the excitations of this stuff that's
Mhm.
everywhere manifest themselves as particles,
Okay.
and those particles are known as Higgs
That's
bosons.
Higgs bosons.
Yeah. So
But we actually haven't found one yet.
so we haven't found one yet. That's right. That's right. So this is still a theory.
Still theoretical.
Yeah, this is still a theory. It's not been observed in
Mhm.
nature yet.
Mhm.
But they built the Large Hadron Collider
Right.
to go look for these
Right.
ripples, to go
Right.
look for these disturbances, the Higgs
Okay.
boson.
Okay.
And yeah, they're you know, tantalizing hints right now that they
Mhm.
might have seen something.
That
It's
was-
not conclusive.
Yeah, that was the news that I had been reading about.
Yeah.
That they're narrowing in on where they think it could be. It's like, you know, they found the building that it's in, but they don't know what room it's in, like sort of getting into it that way.
Mhm.
One of the, like whatever, and I've heard that explanation before, and I've tried to wrap my head around this Higgs mechanism, Higgs field, and somewhere in the back of my mind, I have this niggling problem with it. Niggling.
Okay. that's
Niggling
fine.
problem that reminds me of the ether.
Yeah.
Right? And as a physicist, you know what that is. But the ether was a hypothetical substance that permeated the universe that allowed light to travel.
Yeah.
Because scientists didn't believe that a wave could travel in a vacuum. It needed something. So they invented ether and went looking for ether. Now, they found that ether doesn't exist, and then they found, hey, light can travel in a vacuum. What makes the Higgs mechanism different from the ether? I'm hoping we've learned something from that. Why is it so? Why are we so sure that it's probably there? Right. That's sort of my nagging question.
So it's a little bit different than the ether. So in the ether, you know, the reason that we don't believe it exists, or
Right.
you know, we've proven
Yeah,
by experiment that it
It's
doesn't
not
exist.
there, yeah.
Is that light travels differently through the ether when you're moving
One way or the
one
other.
way or the other.
Yes.
But the same is not true of this Higgs field.
Okay.
Okay, so it looks the same no matter how fast you're moving or in what direction you're moving.
In grade 12 physics, that's one of they talk about, is it the Michelson-Morley experiment?
Yeah,
that
Michelson-Morley
proved that it
experiment,
didn't exist,
That's right.
right? By looking for the movement changes.
Yeah, that's
So we
right.
don't see that with mass because mass is the same no matter which direction or mass
Yeah, either has
doesn't
mass
change.
or it doesn't.
If it has mass or it doesn't, right?
Yeah, that's right.
Okay, so that's one of the pieces of evidence that say that this is different.
That's right.
Okay.
That's
Okay.
right.
Fascinating. Awesome.
Just to kind of bring it back to something for some of the students to be inspired about you and what you do, and certainly as I'm listening to you talk and Colin ask you questions, it is very inspiring, and it must be very inspiring to you to come to work every day to try and find some answers to some of these questions. I'm wondering a few things though, Matt, just about you know, how you carry out your daily activities, and most importantly, what is it about your job or about your research that keeps you coming back every day? What are you working on that's that inspirational piece that you're trying to find an answer for?
I mean, I get to do exactly what I want. So you can't really beat that.
We're doing that right now, aren't we, Colin?
Some of us are getting paid.
Oh, right.
Some of us are.
I mean, I have questions that are intrinsically interesting to me, and you know, I find really fascinating. I really want to know what happened.
Right.
I want to know what happened in the early universe. I want to know how we got here.
Mhm.
And you know, my job allows me to come in every day and try and answer those questions and move in whatever direction that I feel like is going to be best at
Right.
figuring that out.
Right.
And what's the most interesting question you're trying to answer right now?
So I want to know if there are other universes.
Nice.
Mm-hmm.
The multiverse kind of theories.
Yeah,
and
yeah.
theory. Yeah.
Yeah, that I think is a really fundamentally interesting question.
Mm-hmm.
And one that surprisingly you can actually go out and probe with observation.
Okay. That was my next question. So, and I've read a bunch of this multiverse kind of theory. So, what would be one observation that would support the idea of a multiverse?
So according to this theory, we live inside a bubble.
Mhm.
Okay, so think of the very early universe kind of like a pot of boiling water.
Okay.
There's the transition in this pot from something like liquid water to something like steam.
Okay.
So when you look at your pot of boiling water, there are all these bubbles that form inside. And we exist inside one of those. Okay, so the universe is undergoing a phase transition from one phase to another.
Okay.
So what's outside the bubble?
Some other stuff. Yeah,
Yeah.
some other stuff.
Okay.
And that other stuff can sort of seep in. And
Okay.
there are other bubbles with which we can collide or overlap.
Right. So what happens when two bubbles together? Is there an observation we can make of the distant universe, which is what you studied? That like I'm picturing in my mind, if I'm inside a bubble and I see like the line of another bubble
Yeah,
where
yeah.
it connects. Like,
Yeah.
is there an observation that we could make that would be kind of similar?
There
to
goes
that?
one.
Yeah. No, that's very close.
Is it? Okay.
That's very close to what you actually do in
Wow.
practice.
So how do you look for that then?
So you use a tool, and this is basically part and parcel of cosmology. This is a big tool.
Okay.
There was a time in the universe far after this epoch that I'm talking
Mhm.
about, where the universe was quite hot, not as hot as it was then, but quite hot. And it was so hot that the electrons and the protons were separate. So the universe was in a phase known as a plasma.
It's a plasma.
And light can't propagate inside of a plasma. But nevertheless, there's stuff in there, and it's interacting, and there's all
Right.
sorts of things going on. And then the universe cools, and very quickly those electrons find protons and make atoms, hydrogen. And all of a sudden the universe becomes transparent.
It's like the fog lifting.
That's right,
Right.
that's right.
Yeah.
And that light just freely propagates. And there's somewhere really far away, really far in the past, that emitted some light, which gets to us today. And we see that. So this is light left over from, basically 13.7 billion years ago,
Mhm.
300,000 years after
Mhm.
the Big Bang. And if you look at the differences in intensity, so that light has different brightness in different directions on the sky, that tells you something about how matter was distributed at that very early time.
Okay.
So it's kind of a snapshot of the baby picture of the universe,
Right.
effectively.
Right.
And if you look at the statistics of those ripples, of those disturbances, you can learn a lot about what the conditions were
Mhm.
in the early universe.
Mhm.
And how you would test for this other
Mhm.
bubble
Right.
is to look for a very particular set of disturbances in this light, so a very
Mhm.
particular pattern of the intensity of the light.
Okay.
And it's exactly like you said, if I think of two overlapping
Sure.
bubbles, it looks kind of like a circle.
Right.
So you look for circles
Right.
in this radiation.
So this radiation now, is this the cosmic microwave background?
This is
that
the
you're talking
cosmic
about?
microwave
Just to
background,
make
yeah.
sure, we're talking about the
Yeah.
radiation. I just wanted to make sure we named it because it's
Yeah.
pretty famous for people.
That's right. You can see it on your TV.
Yeah.
You can see it on your
some of the
TV.
static.
Okay.
Yeah, some of the static on your TV.
So some of
I
this.
always thought that was dead people talking in the background.
Yeah,
That's a
that's
different movie.
Oh, that's
So is this some of the stuff you model then, like what the cosmic microwave would look like if, for example, bubble hit here, then I should see this here. Is that sort of the modeling part of what you do?
Absolutely.
Okay.
Yeah, absolutely.
Wow.
And so, then you want to know if you can test it. So,
Mhm.
yeah, you model it, you make a fake set of data,
Right.
and then you design a set of tools and you try and look for this stuff.
Mhm.
And then you decide if you can see it or not, and then you go and you look at the real data from the
The
cosmic
universe is the
microwave.
ultimate test. Does
Yeah.
it exist or not? Reality always wins. Doesn't matter what we come up with. Reality is the ultimate judge of our ideas, right?
That's right, that's right.
Awesome. Fascinating.
Matt, last question for you before we wrap up. This what's really been an exciting show. Colin.
This
It's
is
a lot
I
of
love
fun.
this stuff.
Message of inspiration for students out there who are thinking about a career in physics or a career in science. How do they get started? What would you advise? And what is your message of inspiration for them?
Well, I guess go to the library. There's fantastic books, and that was, one of the reasons that I did start, early on to get into this stuff.
Don't just Google everything you mean?
Yeah, actually open, the physical book and sit down and spend some time thinking about it's really fun to think about. It's not like you're putting in time, it's studying or something. It's really fun to think about.
It is, and that's
stuff.
something that I think, I'm going to use that word, that we don't spend enough time on is thinking through problems, talking through problems, discussion-based problem solving with peers, because you're right, that then promotes that way of thinking about how to solve problems and getting interested in things. So it's spending time is important. So
Yeah,
that's
yeah.
a great message.
I mean, just ask questions. That's what science is. It's asking questions and figuring out, the best possible ways to answer them. It doesn't have to be physics or the origins of the universe or whatever. It's really just, analyzing the things you see around you, being observant in your everyday life, and looking for things that you find really intrinsically interesting and fascinating, and just keep asking questions about those things. And I don't know, it's fun. It's just fun. I mean, that's really the bottom line.
Awesome.
Yeah.
Matt, thank you so much for coming on the show today and spending some time with us. We appreciate it.
Appreciate it.
Matt Johnson, everybody, postdoc, cosmologist here at the Perimeter Institute in Waterloo, and we thank him for his time. And join us again next week on another exciting episode of This Week in Science and Education. On behalf of Colin, Jagoe, this is Kevin Cougler from Virtual Researcher on Call. Thanks again.